play day. All right, we have 8.2 confidence intervals for one population mean when sigma is known. This is notes for Unit 4, last formal notes for Unit 4. So we have this procedure. It's nice to have a procedure to look back on because it's going to list out step by step how to calculate our confidence intervals. So first of all, what is the purpose of a confidence interval? And that's listed right here. It's for us to find, what is the purpose of the procedure? It's to find a confidence interval for the population mean. Right, so the purpose is to try and estimate a value for the population mean. There's a few assumptions that need to be true in order for us to proceed with this procedure. First of all, you need to have a simple random sample. So like we did with the marathon runners, this is a perfect example of a simple random sample. We took strips of paper to represent each runner, threw them all in a box, and you randomly pulled them out. That was a simple random sample. Normal population or large sample. So large is very broad, but we actually know a number that goes with large sample size. Does anybody remember that number? 30. Good. So as long as the sample size is 30 or greater, then you can use this procedure even if it's not a normally distributed population. And finally, sigma has to be known. In other words, that value will be given to you. So here's the steps. There's 3 steps. 1, 2, 3. And I kind of debated as I wrote these notes whether or not to go to the full depth of this topic, and I decided earlier today I'm just going to go to the medium depth. I'm not going all the way. So if you want to know the full depth of this topic, I'm glad to share that with you on a flex day. So we're actually going to, we have some new kind of symbols involved in this procedure, and we're kind of going to just change those out for something a little simpler since we haven't really discussed the 1 minus alpha confidence level. So instead we're going to say for a confidence level of, you can cross this out, for confidence level of 90%, 95%, or 99%. And we're going to cross out, it says use table 2. Table 2 would be our z-score table, the blue chart. We're going to cross out table 2 part to find z sub alpha over 2. We're going to cross all that out. And we're just going to write the table below and draw an arrow. We're going to just use this table right here. So that's step 1. Step 1 is to realize what is the confidence level and what is the associated critical value. So we're not considering these z sub alpha over 2 values. We're considering them, and it's really interchangeable. There are critical values, or CV, and you can see CV, it says critical values underneath, right there. So that's step 1, figure out your critical value. Step 2 is to find the confidence interval for mu, which is x bar minus, we're going to put a CV here, critical value times sigma over radical n, all the way to x bar plus z sub alpha over 2 times sigma over radical n. So I'm going to rewrite that over here to the side. For our confidence interval, we're going to do x bar plus or minus CV times sigma over radical n. And this should look familiar. Sigma over radical n, that's sigma sub x bar. Same thing. So this is our step 2. Calculate the confidence interval. And we're still learning CV, that's critical value. Step 3 is interpret the confidence interval. That would be to say something like, we can be 95% confident that the population mean will fall within any one of these confidence intervals. The population mean would fall within any one of these confidence intervals. Note, the confidence interval is exact for normal populations. So this method works really well for normally distributed populations, and approximately correct for large sample size from non-normal distributions. That's where your sample size is 30 or more. It's pretty close to being exact. Now here is a fundamental principle of data analysis. These are basically like rules of good practice for when you're doing data analysis. Before performing a statistical inference procedure, remember that inferential statistics? So we're doing a procedure about inferential statistics. Before you do any kind of procedure, you must first examine the sample data. So if any of the conditions required for using the procedure appear to be violated, do not apply the procedure. So these would be our conditions right here for applying the procedure. Instead, use a different, better method. So back down here to this chart. You can see 3 different confidence levels. These are the most popular ones. These are the ones you will hear most often in the news, in any kind of media coverage. A 90% confident, we're 95% confident, or 99% confident in our interpretation of this data. Okay, so it's a pretty common actual use. Now we can kind of ignore this column right here for a 90% confidence level, and we're going to round these to the nearest tenth. The critical value is 1.65. Hundredth, what did I say? Sorry. To the nearest hundredth. And then for a 95% confidence level, you recall we used 2 in section 8.1. We're going to be a little bit more specific and use 1.96. So the confidence level, or the critical value for a 95% confidence level is 1.96. It's already kind of rounded for us. And then 99% confidence level, we're going to use a 2.58 critical value. And confidence level, we're going to abbreviate CL. So when you see CL, that's talking about how confident we are, 90%, 95, or 99%. This is where I was making the notes and thinking I would go to that deeper level with you, so I can fill that in with you on another day if you want. Flipping over for example, civilian labor force. I always think it's interesting to look at actual data. Our source here is the Bureau of Labor Statistics. So a lot of times it's pretty common to see articles in the newspaper or news sources that reference labor statistics. And in this case, the Bureau collects information on the ages of people in the civilian labor force and publishes the results in Employment and Earnings. So it's probably a magazine. 50 people in the civilian labor force are randomly selected. So we have 50 people randomly selected, right? Randomly selected is one of our conditions for using the procedure. Their ages are displayed in this table. Find a 95% confidence interval for the mean age, mu, of all people in the civilian labor force. You see here we have a 95% confidence interval. That's important because 95% is our confidence level. Assume the population standard deviation of the ages is 12.1 years. We're given sigma, also important. So I'm going to kind of write those things down. And this is how I like to do these problems. While I'm doing Math Excel, I should have a piece of paper handy and be writing things down. N equals 50. That's my sample size. I know sigma equals 12.1. And I also know my confidence level is 95%, which I can then check my table to find my critical value. My critical value for a 95% confidence interval is what? 1.96, real close to 2, right? These are ones, that's a table you actually will want to memorize. And it's not hard. Once you start using them repeatedly, it kind of gets stuck in your head anyway. So we're going to do 2 parts to this. We're actually going to do the 95% confidence level, and then we're going to do it again for a different confidence level. So let's first write out our formula. Confidence interval will equal x bar plus or minus the critical value times sigma over radical n. And then we plug in our values. X bar, oh, we don't know it, do we? Okay, go ahead and calculate the mean. Shelby said it's 36.38. That was really fast. Thanks, Shelby. And the critical value is 1.96 times 12.1 over square root of 50. So this is what I want you to do with me. I've noticed some people enter this in different ways, and there's a way that's a lot more efficient than other ways. So I'm going to show you how that goes, because using a graphing calculator is kind of a skill in itself. I take for granted that I've been doing it forever, so I want to clue you in on some tips. So we're going to enter this in all together, 36.38 minus, I'm going to start with my lower bound, because that's the one I write down first, minus 1.96 times 12.1 divided by the square root of 50. And then you can press enter. Right, I was actually talking to someone who's a freshman in college this year, and she said, I can write the right numbers in the right places, but when I go to calculate it, for some reason I get the wrong answers. That happens. And your problems get longer when you take your freshman college course. Some of you will only have to take 1 math class in college. But being able to use your calculator is actually a skill that you'll really appreciate then. So 33.03 is our lower bound, so that's an age, so our mean of our population would fall between 33.06. Now we're going to go up. Press your up arrow. Yeah, I did. Thanks. This is when I wish I had used a pencil. 33.03. 2. I'm going to go up. So in your graphing calculator, you want to push the up arrow until you're highlighting what you had just previously entered, and press enter. And it will reappear, and the only thing you need to do is scroll over and change your minus sign to a plus sign. And enter. 39.73. Makes things go a lot faster. So then we want to interpret this information. So we would say that we can be 95% confident that the population mean, I could write that whole phrase out, or I could just write mu, that mu lies within our confidence interval or you could say CI. Part B. Let's shoot. Do you want to go with 90% confidence or 99%? 99? Anybody feeling 90? You want to fight? Okay, 99? Okay. So we're going to go with a confidence level of 99%. So what would our critical value be? 2.58, good. So now we just repeat what we did in part A, right? Our confidence interval is same mean. Only thing changing here is our critical value from 1.96 to 2.58. Same population standard deviation, same sample size. The nice thing is we've already got this entered in our calculator. We can go up, press enter, scroll over. I want to change the plus to a minus sign and change the 1.96 to a 2.58. So 31.97. Same thing, scroll up. Tell me when you've got it. If you're on an old school calculator, the way to scroll up, you press second enter. I would recommend using that TI 84 plus calculators. They're just a little, they're just a little bit more advanced to allow us to do these things. What'd you get, Madeline?
36.38.
Okay. Anybody else want to verify?
40.
Oh, okay. 40.79.
The calculator did like some weird thing with the square root for some reason.
Oh, okay. Huh. All right. So when we had a 95% confidence level, what was the length of our confidence interval there? You can find that by just subtracting. I'm just going to make a note of that. What'd you get, Shelby? So if we just subtract 39.73, and you could really just probably do that in your head. Yeah. The length is 6.7. Down here in part B, what's the length? Just subtracting the 40.79, 8.82. So what happened there? Comparing the length to the confidence level. The length is smaller when the confidence level is smaller. Okay, so we had a 95% confidence level and we had a 6.7 length. And then when we had a we increased our confidence to 99% and the length of the confidence interval increased. Okay. Yeah. And kind of the way to think about that is we want to be more confident, so we kind of need a little more wiggle room. So if I wanted to be 100% confident about the ages of people in the workforce, I could say I am 100% confident that the population mean will fall between 5 and 150. Age 5 and 150. There's no one in our workforce that is age 5 legally, and there's no one living today that is 150. So I pretty much got it, right? Like there's no way that the population mean is not within that range. So kind of on a dramatic scale, you can imagine why as we get more confident, we just need more wiggle room. And that's exactly what this says, confidence and precision. The length of the confidence interval is what we're talking about when we say precision. So for a fixed sample size, decreasing the confidence level improves the precision or makes that length smaller. And you can see that here. For the 90%, so we didn't do the 90%, but it's here. You can see 33.6 to 39.2. And then for the 95%, we did that one. It was 33 to 39.8. And then if we were to put the 99% down here as well, we would go down to 31.97 to 40.79. It just gets bigger with more confidence, higher confidence levels. All right, I want to point something out about the margin of error. Okay, that came up a little bit in 8.1. So the margin of error is the length here. We call it E. So the margin of error is here and here. We call that. Okay, thanks. Margin of error, E. So you can see the length of this entire confidence interval. The length is 39.8 minus 33, so that's 6.8. Huh. Well, they rounded differently than us, so 6.8. So the margin of error, you can see, is the distance from the mean to the lower bound as well as the distance from the mean to the upper bound. So it's half the length of the entire confidence interval. So the margin of error here would be 3.4. Okay. Also, in our confidence interval equation, CV times sigma over radical n. That's this part right here. Right? You got your mean. The confidence interval is made up of the mean plus or minus the margin of error. So you could rewrite this as CI equals X bar plus or minus E. So that's your notes on confidence intervals for one population mean for the 90, 95, and 99% confidence level.